Today we'll continue our discussion of angular momentum and multiparticle systems with an example. Recall from last time that we can always think of the total angular momentum of a system of many particles as a sum of the system's translational angular momentum associated with the motion of the system's center of mass and its rotational angular momentum associated with the system's motion around its center of mass. We also covered the special case where the system is rigid, meaning the particles don't move relative to each other, and discovered that in such a case we can write the system's rotational angular momentum as the product of its moment of inertia and its angular velocity. Now, the moment of inertia of a rigid body depends on how all the mass in the system is arranged. For a rigid collection of point masses in a plane, the moment of inertia about the center of mass is just the sum of each mass times the square of its distance from the center of mass. For continuous masses, we can find the moment of inertia by solving an integral with a particular result for each different shape. In this course, we'll just use the results for some simple shapes like disks, cylinders, and spheres. Let's do that right now, using a certain solid sphere which most of you should be acquainted with, the Moon. The Moon orbits the Earth in a more or less circular orbit, which for this question we'll take to be perfectly circular. Let's say the Moon's axis of rotation is perpendicular to its orbital plane, which we'll call the xy plane. In this problem, our system is just the Moon itself. The mass of the Moon is 7.3 times 10 to the 22nd kilograms. The Moon is 3.8 times 10 to the 8th meters from the center of its orbit, and its own radius is 1.7 times 10 to the 6 meters. The moment of inertia of a uniform solid sphere rotating about its center of mass is 2/5 m times r squared, where r is the radius of the sphere. Let's find the total angular momentum of the Moon, which we recall is the sum of its rotational angular momentum and its translational angular momentum. To find the translational angular momentum, we need to know the angular velocity of the Moon's center of mass as it orbits. It's pretty clear that we should choose an axis which passes straight through the center of the orbit for this. To find the rotational angular momentum, we need to know the angular velocity of the Moon's rotation about its center of mass. What are these angular velocities? It might yet appear we don't have enough information to solve this question, but we do. Sometimes in physics problems like these, you'll be expected to supplement the information you're given with things you already know about the world. Let's do that here. The Moon completes a full orbit around the Earth in 1 month. That's actually where our word month comes from. We know the period of the Moon's orbit is 1 month because the phases of the Moon's cycle from full to new and back to full again in 1 month. This means the Moon is orbiting the Earth as shown, with the sunward side illuminated and the other side dark. Let's say that a month is just 30 days long and express that time in seconds. The angular speed of the Moon's center of mass is just one full orbit, 2 pi radians, divided by the period of the orbit, 1 month, about 2.6 million seconds. The right-hand rule tells us which direction the angular momentum points. In this example, out of the screen, in the positive z direction. Now that we have the angular velocity of the Moon's center of mass in hand, we can figure out the Moon's rotational angular velocity by exploiting one more piece of knowledge about the Moon. The Moon always keeps the same side facing the Earth. This means that the Moon must rotate about its center of mass once every month. It must rotate in the same direction as its orbit. This also means that, by the right-hand rule, the rotational angular momentum points in the same direction as the translational angular momentum. That is, if from our perspective the Moon orbits around the Earth counterclockwise, then it must also rotate around its center of mass counterclockwise. The angular speed of the Moon's rotation around its center of mass is therefore 2 pi radians divided by 2.6 million seconds, just like the angular speed of its orbit. The right-hand rule tells us which direction the angular momentum points. In this example, out of the screen, in the positive z direction. Finally, with all of these pieces together, we're set to figure out the total angular momentum of the Moon. What is it? The correct answer is shown here. To find the magnitude of the rotational angular momentum of our system, the Moon, we find the product of the Moon's moment of inertia and its angular velocity around its center of mass. We find the direction of the rotational angular momentum with the right-hand rule, curling our fingers in the direction of the Moon's rotation. The result points into the screen. To find the translational angular momentum of the Moon, we mentally collapse the whole continuous mass of the Moon to a point mass located at the center of mass. This is the point particle model. And multiply the point particle moment of inertia by the angular velocity of the center of mass. The right-hand rule shows us that the translational angular momentum points into the screen too. The total angular momentum is just the sum of the translational and rotational angular momenta, since they both point in the same direction, and only along the z-axis. We can add the z components of these two together to get our final result. One final note. The fact that the Moon rotates once about an axis through its center of mass as it revolves once around the Earth is rather special. This type of motion is sometimes called tidal locking. The results of our discussion here would carry over to cases where the orbiting celestial object moves a little less rigidly, in that the object may revolve in its orbit and rotate about its center of mass at different rates. For example, Jupiter completes one orbit about the Sun in about 11.8 Earth years, but rotates once about its axis in about 10 Earth hours. In the case of Jupiter, both the translational and rotational angular momenta are, for the most part, perpendicular to the orbital plane, so the direction of the total angular momentum would be also perpendicular to the orbital plane. However, there are other cases where the direction of the rotational angular momentum is quite different from the translational angular momentum. For example, the Earth's rotation axis is tilted about 23 degrees from the direction of the orbital axis. And so it's quite possible to have physical situations where the total angular momentum, the translational angular momentum, and the rotational angular momentum do not all point in the same direction. These cases are important not only at the celestial scale, but also at the atomic scale. We won't discuss such cases further here. However, we mention this as you might expect to run into such cases in future courses.